Hello, everyone. Greetings, salutations. This is Volts for February 6, 2026. So, how's the climate doing? I am your host, David Roberts. I began my career as a journalist in the early 2000s, and the online climate wars of that era were formative for me. My first brush with fame was when Rush Limbaugh mentioned me by name on the radio over something climate-related, which brought me a torrent of angry emails. Mercifully, this was before social media. However, by the mid-2010s or so, I felt like I knew what I needed to know about climate change. It looks bad. We should probably try to prevent it. And so I turned my professional attention toward clean energy, which was beginning to get cheap and viable. I haven't really followed climate science closely since then. In the wake of the MAGA backlash and Trump's victory in 2024, climate has precipitously fallen off the political agenda. Trump has pulled out of the Paris Agreement, withdrawn from the UNFCCC, dismantled climate science research programs, banned the use of the words climate change in government documents, and so on. Meanwhile, Democrats seem to have vowed to say nothing but the word affordability. So I was just wondering, has anything happened in the world of climate science that should make me less concerned than I was back then, or more concerned? What is the science saying these days? What has happened in the last 10 to 15 years? I thought it would be a good time to touch base with an actual climate scientist. So I have with me today Dr. Sarah Kapnick, previously chief scientist at NOAA, and now the global head of climate advisory at JP Morgan Chase, working at the intersection of climate, risk, and finance. We are going to do a check-in or a level set or whatever you call it. What has happened in climate science lately, and just how freaked out should we be about it? With no further ado, Dr. Sarah Kapnick, welcome to Volts. Thank you so much for coming.
Thank you so much for having me for this discussion.
Dr. Kapnick, I'm particularly excited to get you for this discussion because I know you are not only a scientist, but your career has been spent translating science for people and institutions outside of science, which means you have a long professional experience answering impossibly broad, dumb questions from people like me. So it just makes you perfectly suited to the job we have ahead of us today.
I would like to say none of them are dumb.
Okay, there are no dumb questions.
It's very important to have curiosity in this space and to talk it through, as we're going to do today.
So here's kind of what prompted me to do this pod. So I would say among people like me, in my basic cohort, you're educated, dim, politically aware, whatever, general demographic, people seem to have settled into this attitude towards climate change that it is grim but manageable. The idea here is, we over time, through concerted action, have sort of taken the truly apocalyptic possibilities, your sort of 4 to 8 degrees of warming type of possibilities, off the table. We're headed for somewhere between 2 and 3 degrees of warming, which is, as I said, grim but manageable. It'll be bad, but it won't be as bad as it could have been. Then I also see sometimes out of the corner of my eye headlines to the effect that the impacts of climate change are hitting faster or sooner or worse or harder than we thought or than we expected, causing more damage than we expected. And I read about tipping points looming or already underway. Some of them are already tipping, which brings me back to sort of freaking out. So I guess part of what I want to do here is just kind of, pardon the pun, take the temperature of where we are at. So I think the place I want to start is I want to talk about what sort of climate scientists have learned over the last 10 to 15 years, et cetera. But maybe the place to start is what hasn't changed. in climate science in the last 15 years? In other words, like, what is the steady core, and are we as confident as we were then about it?
I would say the steady core is that we have observations of what's happening in climate. We have temperatures and stations around the world and satellite data in the ocean that are showing a steady rise in temperatures over time. And that is linked to the rise of greenhouse gas buildup in the atmosphere. Additionally, we don't just have the measures of that we're monitoring what's happening on the climate through observations. We actually also have physical-based models, so models of the climate system that allow us to see that change in over time and be able to see it in the models and why it is happening and how it varies in time, and then also project into the future that if you continue to have greenhouse gases accumulate in the atmosphere, that you will continue to have temperatures rise. And then a host of things come from that in terms of changes in extreme precipitation, changes in glacier size, changes in temperatures in the ocean, and then further impacts on ecosystems, and then a growing body of research around how that affects society. But the basics of it, of temperatures are rising, they're linked to greenhouse gases, that is fundamental to it. And the expectations of that into the future, the response of temperature, pretty steady in terms of our expectations of how it's going to continue to warm.
And one of the things, I was thinking about all these old fights, these sort of take me back to a previous time in my life, but there used to be a lot of fights online about the models, the climate models. This was a big thing, various people accused the models of weighing things or putting their thumb on the scale. There's a whole fight over the hockey stick thing. I barely even remember the details of that one. But I guess what I want to know is the basic models that were developed sort of in the 90s and 2000s, have they held up pretty well? Like, are we now observing what the models said would happen roughly?
We are, to put it very bluntly. And those models have continued to evolve since the 90s, since they were developed, and they've become more complex, and they allow us to ask more questions about how climate impacts weather and ecosystems and more local scale issues. But zooming out, large scale perspective, those models have been very steady, and the amount of temperature that will rise with the amount of greenhouse gases that have now accumulated in the atmosphere.
So we had it pretty right.
We did. Actually, a few years ago, when Suki Manabe, the Japanese-American scientist who helped build the first climate models in the US, when he won the Nobel Prize in Physics.
Right, I remember
and
that.
I remember at the dinner for him held in Princeton that I went back for, he said, we learned this and we are now seeing it. And they were right. They were right in the time and the way that those were constructed. They're fundamental physics that have led us to today. And there's new science and new information that is coming in that we will talk about. But the base understanding of what was predicted with the amount of emissions that we've seen and the accumulation in the atmosphere is what was expected within the bounds of expectations.
It's kind of funny. Those early scientists were so right about the science and so wrong about what they expected to happen socially when they produced a bunch of good science. They were like, isn't this the part where you take the science and do something about it? Their predictions on that front were very wrong.
We all have our skill sets. And unfortunately, I think there was an underestimation of the difficulty of understanding what all the impacts in society would be and the behavioral science of how people might react and all the myriad of ways that we are now living through and learning and seeing at this point in time.
Yes, I'm not sure anyone's really mastered that skill set completely.
Well, when I first learned about it, and I was working on Wall Street over 20 years ago, and I wanted to have this career at this intersection of climate risk and finance, I thought surely that we would be where we are today in better understanding of climate and its intersections on insurance and on other things. I didn't think it would take 20 years, the level of evolution that I'm seeing now, and I have the job that I thought should exist back then now. But that's because with the science and with clarity of what you think the world can look like, you can start thinking about what that means. but not everyone is going through that thought process. Not everyone has the same views of how society will react or how markets will react. And so there's a lot of uncertainty in the translation of that science and the use of the science. And then when do markets react?
Indeed. So when people talk about the scientific developments of the last 10 to 15 years, one thing that comes up a lot is what's called attribution science. So for listeners who don't know what that is, it's what it sounds like. It's the science of trying to attribute specific weather events to climate change. So if a giant hurricane comes along, it used to be, I remember in the early 2010s, again, going back to that time, it used to be a big hurricane would come along, a bunch of people would come out and say, hey, look, there's climate change. And then a bunch of people would come after them and say, now, we're not allowed to attribute any specific weather event to climate change. It's too fuzzy for that. It's all probabilistic, et cetera, et cetera. I used to get scolded about that all the time. And then sometime around like 2020, I basically started reading these headlines saying, hey, guess what? We can do this now. So I guess I'd like to hear from you a little bit more about what is attribution science and why has it had this seeming breakthrough now where it has such confidence now of tying specific events to climate change.
Yeah, as a journalist, you've really lived through the evolution of the science and then being able to talk about that science and what it means as you look at weather events. So climate attribution science really has developed over the last 10 years. The first paper on it was after the heat wave that happened in 2003 that went across Europe that led to thousands of deaths. And the analysis there was showing what was the likelihood of that event when it happened, what was the likelihood of that event happening in the past based on observations, and then also using models to try and understand how is that risk evolving in time. And the reason the science has now evolved and people are making claims about how those risks are changing in time and how much climate change has changed the risk of individual events is because, number one, we've now had enough climate change occur that you're actually able to start parsing, in a technical term, the statistics out, where you can actually say this event has a much higher likelihood of happening now in the past because of all the climate change that has happened to date.
Your sample set has grown.
It's the sample set, but it's also the signal is now separated from the noise. So
right.
You have variability in these extreme events. The extreme events, they happen by definition very infrequently. So it's also really hard to quantify what is that likelihood in time. But now you've had so much climate change occur. And when you actually have these events occur, the buildup in multiple of these events in short periods of time and change in that over time is now you're able to actually say, no, this event is now happening with greater frequency, and this is how the frequency has actually changed over time. And it's not just in the observational record, it's also now there's in the physical based models, the ability to generate hundreds, if not thousands of years of the data to be able to say, what should a year like this look like and the extreme weather look like in a world with X amount of greenhouse gases in the atmosphere. So now you can also, using that technique, create thousands of years of data, which then allow you to quantify what the risk is today and what it was in the past, what it is in the future, and be able to make those statements of climate change has altered the risk of this event by this much, and this is why, and you can also explain why. And so it's the fact that you've had enough climate change to be able to see it in the observational record, but then also these modeling techniques and the availability of supercomputing systems that it allows you to do this.
That was going to be my question. I know there's more data to work with, but also I was wondering how big a role the sort of advances in just raw computing power have here. Like I assume you can run more models more often these days just because of computers.
Exactly. So it's more models, more data. But then actually I'll add to that as well that over the last 10, 20 years, there's also been a shift that the physical-based models used to be very coarse in resolution. So you would look at climate over a box that was 300 kilometers by 300 kilometers like 20 years ago.
Spatially coarse, you mean?
Yeah, spatially coarse. But now you can look at it at blocks of 25, 50.
Oh, interesting.
on each side. And so that also actually lets you look at these extreme events, which also may be very local. And also now adding on to that now and the revolution that's happening right now in weather and climate modeling, now with also AI techniques, it allows you to take all those data sets and create new synthetic data sets with the spatial scales of the extreme events to be able to further explore them. And so all of these scientific advancements over the last 10 years, 20 years, plus all the climate change that has happened, allows us to actually ask these questions about risk and how that risk is changing in time.
It seems to me like no matter how good this gets, we're probably never going to develop the ability to predict events that are sort of by definition extreme outliers.
There are prediction capabilities in weather.
Right, weather-wise, but I mean like climate-wise, like years.
Well, there are certain things that you can predict on a seasonal basis, which is a couple of months out to 2 years. Like heat waves have some predictability, large-scale droughts. I did a bunch of research years ago on snowpack and on hurricane numbers, and the barrier to that is roughly 2 years. And there's actually science that's decadal prediction looking out 5 years and longer. And at a really large scale, that type of information really is ocean temperatures and heat waves. But with AI and machine learning, actually, there's more and more analysis trying to show predictability at those longer timescales and understand them. And I think it's a really exciting area of science development.
Slightly a diversion, but I've always been curious about this and you sort of raised it. So I thought I would throw it out to you. Among scientists, is there the thought that with sufficient data and computing capabilities, we can sort of capture the climate and predict it sort of completely at some point if we have complete data? Or is there an element of unpredictability and uncertainty that is irreducible? Practically speaking, this doesn't really matter, but like, I just wonder, like, at the limit, is this an understandable system with sufficient computing power, or is there an element of kind of chaos to it that will never be sort of reduced or eliminated?
There are certain things that we think that we will be able to predict and certain things that we won't, because ultimately it's chaotic, but also the very definition of did you predict something or not, particularly for those systems that you know are chaotic. You would give a forecast of the future that's broad. And if you fall within that broad analysis, was it correct or was it?
Right. It's all about granularity, I guess.
Yeah. And this is where there's difficulty in explaining predictions and how to use them. And does something fail or not? That also, I think, in the communication of all of it is why it's been so difficult for people to understand how to use the information in their daily lives and their businesses and others, because the communication of all of this, particularly of predictions that are good or not, and what do we know, what you don't know, and how does that change in time, is very difficult to discern, not just for the average person, but even for very sophisticated people. And that's, in my day job, that's what I spend a lot of time doing, is explaining the probabilities and statistics and trying to translate what it means and where those sources of uncertainty come from, and then what that means as you chart a path to plan for the future.
Yes, as you and I discussed previously, decision-making under extreme uncertainty is not something I think that humans are naturally very good at. They need lots of help. But one of the things I wanted to ask about this attribution thing before we move off it is, has it reached a level of confidence that its results could theoretically be used in, I don't know, court cases, for instance, or insurance proceedings, for instance? In other words, could we go to court, like if a giant hurricane happened and science says this happened because of climate change, like is that information solid enough to be used in sort of legal and financial and economic settings?
It is starting to be tried in courts, and people are using the attribution science to argue of physical impacts are changing, and those physical impacts that have financial impacts lead to loss, which then are put into court. And these are happening around the world. And the science of attribution will continue to get stronger as long as climate change happens and more climate change affects these events and as those events are realized. So some of the court cases actually that have come through have tried to say an event will happen to me in the future that will lead to a loss, so you should pay me today so I avoid that loss.
Oh, interesting.
And in some of those cases, what's come to pass is, well, you have to experience the loss before we bring the case. And so they were thrown out, not because necessarily the science, but because the loss hadn't happened yet. So it will get more, we should revisit this question 10 years from now when we have more climate change, when you see more financial losses due to events. We'll see what happens in litigation. And I should say this litigation is happening all around the world. And there's various trackers that are tracking where that litigation is happening and what the nature of them is and what types of events are following. But fundamental to all of it is the science of knowing how risk is changing over time. And that science is going to continue to improve. And part of the reason it's going to continue to improve is just because with each additional ton of CO2 in the atmosphere, it is going to lead to more climate change.
And have we had an example yet, a clear-cut example yet, of a particular party being held legally liable for a particular climate damage based on this attribution science? Or is that still to come?
I am not aware of all the court cases, but
many.
Will say the ones that I've been following so far has not seen that.
Interesting. Well, it's definitely something to watch. So that's one of the things that's come along in the last 15 years. The other thing that seems to have developed or come along quite a bit, or at least I see a lot more headlines about it, a lot more discussion about it, is this notion of tipping points. So again, like I've been through some cycles with these things. Like in the beginning, tipping points were these big, scary sort of giants in the distance that kind of, they are what put the existential in the phrase existential risk, right? They are the ones that could truly be catastrophic and were part of what got everybody so scared about climate change. And then I felt like there's a little pushback from the scientific community basically saying like, everybody calm down a little bit, dial your rhetoric back a little bit. Like these are big, scary things, but they're very low probability. There's no reason to think they're imminent. Everybody chill out a little bit. And then now I feel like we're coming back into a cycle where they're back. Like the big, scary giants are back. And furthermore, we understand them better. And furthermore, it looks like some of them are happening right in front of our very eyes. So help me wrap my head around how I should feel about tipping points. What is the state of the science there?
I think you've gone through all the emotions of many of the scientists and the communicators in the space as well through your arc. So I think I should start with the definition. And the definition I wanted to give, a simple definition of climate tipping points. You should think of them as these critical thresholds in time in a part of the Earth system where just an additional amount of warming from climate change can trigger then a really large, and it can be abrupt and potentially irreversible change to a totally new state.
And when I think about tipping points, the key feature for me is that once that starts, once you sort of, the straw that broke the camel's back, you put that last additional ton on and you flip the system. Once that change starts, it's unstoppable, basically. Like that's what is scary to me, is that once that's underway, no matter what you do about emissions, you're basically out of control of it. Is that accurate or is that too theatrical?
So each tipping point can be different in its behavior. And
yes.
Actually, that's as a scientist, curious about studying them and what they look like. For some of them, like from glaciers, in the past, we've seen these abrupt changes where you have glaciers grow or they're stable and then suddenly they decline really rapidly or then they grow really rapidly. And you can see it in the records that we have in the past. But then also in the models and the modeling capabilities, if you run many, many, many years of looking into the future when you might have something like this, like changes in ocean circulation and how quickly does it happen or how sticky is it? Does it ever reverse? And why does it reverse? You can find sometimes these things happen abruptly or they happen in many of the simulations, but there also may be times when they don't happen when you're running it the same way. And so that's part of the messiness of the communication of these things.
Well, that just makes it scarier to me. It's like these big, like I said, these big looming scary giants that like sometimes disappear in your peripheral vision, but then sometimes reappear, like the fact that we can't pin them down or predict them precisely makes them scarier to me, I guess.
Yeah. And I think what you also said with you heard about it, then it went away, and some scientists seem to be fighting, and then it's back again.
Right.
There are these deep debates about some of these, about what will trigger them, when they'll be triggered, how fast will they happen, will we know when they're happening, will they be irreversible? And actually, so there are these unknowns of these things. And actually, there's now certain science programs, either done by philanthropy or done by governments or within universities, that are starting to ask those questions. Like the ARIA program in the UK has actually been funding sensor technology and creating observation systems, saying we need to know if these things start to happen.
Yeah.
And also funding, if they start happening, how might you reverse them? And as information about that has gone out, I think that also adds to the uncertainty of the general public of saying, what do these things mean? I thought you said it's definitely happening and it's irreversible. Now you're also saying that we might be able to prevent it, and you're looking into the technologies to avoid it. So there actually is a lot of research around these things to better understand and pinpoint. And to get back to your original question, predict when they happen, understand why they're happening, and then figure out all the ways to avoid them.
Is this an area where the science itself has improved though? Because it's in a sense, it's kind of like it's hard to study. You're sort of defining the thing that you're studying while you're studying. It's kind of difficult to do in real time.
Although that's also science.
Yes,
it's constantly evolving, constantly asking new questions and trying to push all of the information forward. The scientist who's really led and is very publicly been one of the science leading on different aspects of identifying understanding, and then also reporting out on advancements on this is Tim Lenton, who's in the UK at the University of Exeter. And they actually put out a regular report on the status of tipping points, of what is known, what isn't known, when they expect them to occur, and describing advancements in the science on them. And we should also expect there's going to be a number of other large international bodies of scientists are starting to write about this in group reports, trying to understand what is the state of this. And that's coming out of all the uncertainty and all of the questions that are arising as the science has developed.
Do we know enough to say with any confidence that any of these are underway? Like the coral reef thing, like everybody keeps talking about coral reef tipping point, and I keep reading that they're unhealthy. Like, is that a thing that's basically underway and unstoppable at this point? Like, are there others that we believe have basically been triggered and are underway as we speak?
The coral reef die-off and how coral reefs are responding to heating and when they're going to have large die-off, that one is in the more near term, and we're observing it with every single large El Nino that occurs. 97, 98 was the first one that showed a large die-off, more around 25%. And then when we had the most recent El Nino, you had over 80% of bleaching event that occurred. And so with each El Nino, you have a background of a warmer climate. And then during the El Nino, you have a spike in ocean temperatures that lead to these bleaching events, and it stresses the coral reefs. And so you can look out into the future about the amount of warming and the warming that will be in the El Ninos to understand how much more stress they're going to be. And with each bleaching event, you hope that they come back, but they don't always come back. And so that's the one that we know the most about being able to predict that going forward, because of the really tight thresholds of temperature under which the coral reefs bleach.
I've also been reading a ton about the circulation ones. I will never remember that phrase as long as I live, but you know what I'm talking about.
The Atlantic Meridional Overturning Circulation,
yes.
Or for short, AMOC.
AMOC, maybe I can remember that. That's the one where I feel like I'm reading in headlines now, oh, yeah, that's happening, by the way. Like this, that's the one I'm seeing people talking about, like maybe being in our lifetimes type of thing. Am I Is that correct? Like, what's the state of that particular one?
That is also correct. And the time horizons that people say that it will slow down or shut down are over. It actually is 2030s and starting to happen now, all the way into past 2100. So there's this wide range of dates. However, we already can observe changes in the ocean circulation of AMOC and what the effects of that, because what the AMOC is the ocean actually moves on a large scale. It has like a highway of water, and that water, in some parts it's sinking, in some parts it's moving to the surface, some it's moving west to east, east to west, north to south. And the AMOC is how it's moving in the North Atlantic, because it sinks really in the farther north where it gets really cold. It sinks down at the bottom, and that's what gives us the jet stream and has the pull of the water that is coming, warm water from the Caribbean up north, and that is what might shut down.
This is the one that's going to plunge Europe into an ice age, right?
Yeah, because you're no longer moving heat from the Caribbean equator up north if this shuts down. And so that heat that is moved by the ocean highway is what makes it warmer at the same latitude in parts of Europe than it is on parts of the US or Canada.
So when we say we see it starting to change, that causes me to feel a great deal of terror. Does that mean that it's underway and it's happening? No matter what we do, can we stop it? Or how well do we understand what's...
Yeah, so right now we are seeing it slow down. One of the ways that we can measure this is because that highway of water actually also changes sea levels locally. And as the slowdown is happening, it's actually increasing sea levels a little bit more on the East Coast. And there have been studies that are tying this to more high tide flooding days that are starting to occur. And so people get fearful of these things because A, it's either something that's unknown, and that unknown creates fear, or it's because it's starting to affect their daily life. It's starting to affect finance. It's starting to affect the operability of infrastructure. And so those flooding days, high tide flooding days that you're starting to see along the parts of the East Coast, that affects operability of ports, being able to use those ports because you have flooding and you have to deal with the water. It affects the use of roads. It affects people being able to get to their jobs. It affects the infrastructure because salt water is corrosive, and so now it's corroding infrastructure along the coastline. So if you get more and more of these high tide flood days, impacting a little bit from AMOC, but also impacting from general sea level rise from climate change, that's when you can start actually quantifying what some of the impacts are of starting to see this.
I mean, this gets to the main question. We mentioned decision-making under uncertainty, which is sort of the core state that we find ourselves in climate. But here particularly, like, I don't know, if I'm a bank in Europe and I hear from climate scientists, Europe might be plunged into a multi-century ice age, and that might happen in your lifetime. Like, I would feel that should affect my decision-making somehow. You know what I mean? Like, if Europe's going to be in an ice age, like, in my lifetime, that's financially relevant to me. But on the other hand, like, the uncertainty bars are so huge, it's just difficult to know what to do with it. Like, it seems like we ought to be acting differently based on this knowledge, but it's not clear to me, like, what exactly we should do. So how do you... when risks are this big and vague and far off and fuzzy and difficult to pin down, how do you make decisions around them?
So there's two different ways that I see this starting to be implemented. There are the groups that have assets or investments or have long-term decision horizons on multiple decades. They're the ones that are talking about this and asking me questions about it the most. And so they're matching their decision timeline to the timeline of when these events can occur. Those people with shorter time horizons of weeks, months, years, they're having a hard time grappling with these issues. And the questions that come out of this are, when is it going to affect me? How do I prepare for it? Will I be rewarded if I prepare for it? And maybe will there be new information that will come to pass that then I won't be as worried about this in the future. So I don't need to deal with it now.
Yeah.
So the shorter time horizon people are really debating what to do. And the way that I talk about it, this in a financial sense, is the big question for companies or investors is, when does the market start repricing these things? When does this information, as more information is known, change?
I was going to ask about insurance, right? Like, this is incredibly relevant, obviously, to insurance, but also so fuzzy. You got to translate it into a number in the end somehow. How on earth do you do that?
Again, it goes to the time horizons of how people are thinking about these things. Insurers, some of them also, because of how they operate like life insurers, they have assets under management that they are trying to make sure that they have certain returns over certain periods. And some of those, like in terms of life insurance, may be decades. And so they're thinking about how might this affect assets and asset valuation. And maybe it's not assets over 30 years, but maybe when more information on these things come in the next 5 years, 10 years, 20 years, maybe certain assets will reprice and be less, will have less returns as a result. And so they're thinking, okay, how do I think the science is going to evolve? And then how do I think the market's going to evolve in response to that? And how do I plan for these things as a result? Or how do I diversify away? If I think a tipping point is in just one region, maybe do I have to diversify across multiple regions and think this through?
Well, it seems to me like you're taking these fuzzy, high uncertainty science, and then now you're laying on top of that equally high uncertainty questions about sociology, basically, about behavior. Like, how are people going to think about it? How are people going to react? Like, part of what you're doing in a market is not just reacting to the science, right? You're reacting to how other people are reacting to the science. It just, again, seems like a hopeless fog. Hey there, everybody. Don't worry, I'm not going to tell you about a new mattress or push a credit card on you. This isn't an ad. There are no ads on Volts. It is supported entirely by listeners like you. If you'll indulge me for a second, I'd like to ask for your support. I started Volts because we're all surrounded by depressing news about climate change and misinformation about clean energy, and it's never been more important to share the stories of the real people on the ground doing the real work of transition, and all the ingenuity and courage and public spirit they are bringing to it. People are hungry to hear these stories, to learn from and find inspiration in them. I've heard from people who changed majors or careers after hearing episodes of Volts, people using it in classrooms and community groups, even state legislators who have passed bills inspired by specific episodes. Sharing these stories matters. It makes a difference. If you have found value in it and want to help me continue doing it, I hope you will join the community of paid subscribers at volts.wtf. It's about the cost of a cup of coffee a month. If you don't like subscriptions, you can make a one-time contribution, leave a review on Apple or Spotify, or just tell a friend about Volts. I am grateful for any and all support. If you're already a paid subscriber, thank you. And now, back to the show. Part of what you're doing in a market is not just reacting to the science, right? You're reacting to how other people are reacting to the science. It just, again, seems like a hopeless fog.
As someone who gets to have these conversations regularly, I would not say it's a hopeless fog. A term I sometimes use is we have a fuzzy crystal ball of what the future looks like in terms of climate.
Right.
It's not perfect, but we have a range and we know generally what's going to happen. And decision makers, businessmen, I've seen it with politicians, with national security experts, they're used to making the best decision they can under uncertainty at the time. And you make that decision. And part of the conversation, particularly around this with so much uncertainty and the large potential financial risks or large potential national security risks that come from it, they also think through, okay, what are the decisions I need to be making today to position myself as new information is known or as the world changes? And based on how I think the world operates now, based on how I might think it operates in the future, they either do, like, what do I think are the potential scenarios? What do I think the general direction is? What do I think the worst case scenario is that I want to avoid? And then they create their framework for making a decision around that. And really, depending on the time horizons, depending on the cost of responding, depending on what their views are of their ability to change course as more information comes in, they make different decisions based on this. And it all comes down to the framework of how do you take the science, translate it, and then how do you put it in your framework of decision making that you need to have?
Well, speaking of that, one of the things you sometimes hear that has improved in climate science is an understanding of kind of more short-term variabilities or the short-term weather extremes. And this is, again, like, when I think back early days, climate science has very sort of chunky understanding. And one of the perpetual discussions was, wouldn't it be nicer if we had more granular information that could translate into decision-making more easily, right? So is it true that we are getting better on a temporal scale, getting more granular in our ability to predict and understand short-term variability, or is that just more computing, or am I making that up entirely?
Yes. Hands down, yes. We are getting better at the temporal scales and knowing what is happening more locally. And that has been part of the weather revolution in the last few decades of improvements in the modeling, compute power, improvements of satellite and observations that go into that to know what the current state is to be able to predict it forward, and then the tools of models to predict it forward. And now, very excitingly, and a reason why we're seeing a lot of advancements in AI weather modeling, that also takes all that data, all that model output, all that information that exists today and builds the AI models, which then can even do it with, once you do the really expensive compute to build the AI model, you can then actually run those for weather forecasts in a really short period of time. And we're also really starting to see the use of those AI weather models in decision making. Like there's a program around monsoon data and prediction in India for agriculture that someone was telling me about the other day. And there are more of these case studies that are coming up that now, because those AI models are now in existence and are building better for being able to look really locally about what the impacts are and predict them in advance, and in advance for very specific types of decisions, not just the physical output, but also the decision output that needs to happen on the impacts. Those are starting to be taken up and used in ways that we couldn't have dreamed about, I would say, even 5 years ago.
Interesting. So improved science is leading to improved resilience. Like we're seeing it actually happen. We're seeing it translate into real resilience benefits.
Yes. And I think we'll continue to see it translate as, unfortunately, events keep continuing to happen and new types of events that we've never seen. People are going to use innovation to figure out how to have advanced warning, early warning systems around these things so they can pre-position assets, do evacuations, prepare to minimize damages,
Right.
and then bounce back as fast as they can.
I was going to ask about AI. So it is like I've seen lots of headlines about AI in weather forecasting because weather forecasting is just a classic AI, like a perfect AI application, right? There's all this data. It's fuzzy. It's
I agree.
Non-linear. But are there other areas, like it strikes me that climate science is full of areas that are like tons of data. You know what I mean? Like you have to run sort of analysis over tons of data, find patterns in tons of data. And that is exactly what AI is for. It's what's good for. Are there other areas of climate science where AI is making a big difference? Like what is the current sort of relationship of AI and climate science?
Now we're seeing it in the development of AI models that can be used and run faster than existing physical models. It's also being used to create more local scale information. I've also been seeing advancements in groups that are taking all of that observation data, taking all the model data, and they're actually creating, this is very technical, new parameterization. So it's like the code that represents a part of the climate system, the Earth system. And it goes into the physical based models. So actually the AI is also being used now to improve some of the model code itself and to find places where if you make changes, you improve model prediction or skill. So it's also even being used to advance the predictive models.
And one of the things you do when you change one of your parameters, right, is you go back and I forget the word for it, but basically you like quote unquote predict the past.
Yeah, called hindcasting.
Hindcasting, thank you for you got all the vocabulary. The hindcasting, like you do a new parameter and you're like, does that predict previous events better than current parameters. And I imagine that whole process is much faster these days with all the computing power.
Yeah, that entire process is faster, and it allows you to do it with the physical models. It allows you to do it with the AI models. It allows you to run them both in tandem and put them together and inform one another. The other areas that are exciting are in when you create these predictions of the future, be them short term or long term. There's also a process called post-processing that you get the data and you get it out, but there's also ways to look at the statistics of that data and the knowledge of that based on previous predictions or projections to look at that data slightly differently to improve skill on things. And that's another area that I see AI being used. I also see it being used on creation of new products or to create new insights from vastly different data sources. And that also really lends itself to AI of how do you recombine various pieces of information to be able to create insights. And that's, I think, the exciting part of the innovation that is coming out of it. And you can see it in the headlines and how they're talking about it at the different AI companies. A lot of them have weather groups or weather models, and it's through that reconnection of information that they're creating new types of products to create insight about what the future looks like and how to respond.
If you just let your sort of sci-fi brain run for a little bit, your utopian brain, it's say that the predictions about the sort of exploding power of AI in the coming years come true, and we have this sort of unthinkable computing power available to us, pattern finding that we never had before. Like where could climate science get? Like, do you anticipate climate science being sort of substantially revolutionized by this rising power of AI? And what, I guess, would that look like? Is it just going to be more and more granularity?
I think that it is going to be more granularity. I think it will speed the ability to bring a lot of information together in a short period of time to make decisions. And I think it will also have the potential to create new types of innovation and new insights. But I don't know yet what that speed of innovation and how much that will change from the past.
Right.
So kind of the slope of that curve, how fast is it accelerating or not, is still a question to me. And I think it's very timely that we're
to everybody.
Well, it's very timely that you're asking this question because I was just reading the Nature paper that just came out on this morning that showed that researchers that were using AI were having more output, but the punchline is it's more output, but it's in a more narrow space. So if that continues, we could see more output, we could see more things that come from it, but it will be along similar research lines. It won't be on more diverse research lines. And so some of the ways that that's been described is we may not make the big leaps forward. We make small incremental change off of what we already knew. And so that would suggest that slope of that curve is not going to increase if AI is used in that way. And so we're still in such early innings of understanding that and having the data to understand how people are using it and how they're changing. And even now, knowing that, I think the scientists that are using that are going to think differently about how they're interacting with AI because they don't want to be super narrow necessarily.
Couple of more straight questions before we run out of time. There's been a lot of talk when I think about climate science the last 10 to 15 years, there's been a lot of talk about methane, about a better understanding of methane and its effects and its lasting effects. And of course, through all these satellites, these cool new satellites, now we can sort of see methane emissions, quote unquote, see them on the ground. And so we now have a much better empirical understanding of where methane is coming from. What's your sort of take on the role of methane in climate science? Like, what's the sort of short story there?
Short stories now, satellites and laser technologies are allowing us to know where the leaks are happening and where they're coming from, the sources, in a way that we didn't have previously. And so that's giving the ability to record how much is going into the atmosphere, where it's coming from, understand the sources, and then be able to plug those leaks. And the reason people care about methane is the additional expectations of how much methane goes into the atmosphere of warming is that it's roughly 0.3 degrees of warming. And so if you stop those leaks from happening, you will cool the planet by 0.3 degrees. You will not have that warming.
more quickly too, right? Like that effect will be felt more quickly than cutting CO2.
Yes, because of how methane cycles through the atmosphere in the Earth system.
But we knew that. So we have a better empirical understanding of where it is and what's leaking it. But has there been any real change in our understanding of sort of how its role in the atmosphere, or is it still we still have a
What I
pretty
would
good handle on it?
say has really changed is thinking about methane reduction as an important strategy for managing global temperatures. And that potentially some of those strategies might be lower cost or could have a near term impact on warming that is significant. And because we now have the satellite data, because there's now boxes of instrumentation that you can put in a location, and like radar, it sends a beam around it and then it can identify where all the leaks are in regions. Because you now have those technologies, you now have the ability to pinpoint where it's happening and be able to then hypothetically stop those leaks. So that's what's changed now is identifying, we can identify it. And so hypothetically you can stop it. But then also the realization that if you stop it and you put dollars towards stopping it, it will have a climate impact. And there's a bunch of analysis too, arguing some of the methane reductions may be lower cost than carbon reductions for other technologies. And so if you're trying to do a cost benefit analysis of different activities to reduce greenhouse gas emissions at large into the atmosphere, pinpointing methane reductions becomes an important part of the strategy.
So it turns out that burning fossil fuels and throwing particulates up in the atmosphere shelters us from some of the warming that we would otherwise be experiencing. Is a perverse benefit of pollution that is otherwise a health nightmare. And so as we've been reducing that particulate pollution, especially on the oceans, all that heating that was held back is coming in. What's our current understanding of that dynamic, and how worried should I be about that? Because the way I read these headlines that like if we solve pollution, we are basically condemning ourselves to like a rapid degree of heating, in a relatively short time period. And that seems like worth freaking out about. What's the state of play there?
I think you'll find in talking to me that I don't freak out about things. I would say
I freak out about everything, so we're a nice balance here.
Fair. We're seeing this real time now, and particularly what you're referring to is that there have been standards around cleaning up exhaust on ships, traversing the oceans. And so as a result, they're not putting those particulate matter out. They're not leading to clouds over the ocean. The ocean is very dark, so it actually absorbs a lot of heat.
Right.
If you have the clouds and you have those particles, instead of the ocean absorbing the heat, it gets bounced back out into space. And so actually over the last decade, we are now unknowingly having an experiment on what does that cleanup do when you actually do it. And that is one of the reasons that's been put forward. And there's a bunch of modeling and a bunch of observations now that are starting to support this, that is coming out, that's why when we saw the warming in 2023, 2024, and when it reached in some of the data sets of 1.5 degrees of warming on the globe in 2023, it was because of this loss of those aerosol particles. And so as a result, discussion now of what does that mean going forward if you reduce further pollution? And so the modeling and the analysis of the observations right now are pointing to that the cleanup of those particles will lead to further warming. And it's on tenths of a degree, it's not on multiple degrees, but it's an important aspect of the modeling that occurs of understanding what the future looks like on a variety of scenarios of greenhouse gas emissions, of aerosol emissions, and how the climate responds.
Well, this gets into a slightly broader thing, which is you repeatedly see headlines saying that warming is happening faster than we thought. Basically, like the effects are spiraling faster than we thought. And so, as I understand it, there's been some argument about like, does that mean the models were wrong, that the models have systematically underemphasized things, or is it just that there are these sort of kind of peripheral one-off things like the particulate thing happening that are sort of accelerating things in the short term, but the models are still basically sturdy? Is it true that we're seeing effects unspool faster than expected, I guess, would be the broadest way of phrasing that question.
As a yes, broadly in terms of some events, if you try and reproduce them and look at them in the climate projections, you don't see them for decades out,
Right.
or we weren't talking about them as an issue. So, like the 2021 heat wave that led to the wildfires, it was called the heat dome that happened over the Pacific Northwest. That was not when people went back and looked at some of the predictions. It wasn't expected for a couple more decades to see that type of thing. And there were two problems of the science of the past. One was we weren't able to use those models for the tools to look at extreme events locally at the way that we can now. So in some ways, you couldn't ask those questions.
Right.
So in looking at what the future looked like, if you looked at it directly, you weren't saying that was a problem. And I would also say we weren't necessarily asking those questions in the decades before. And so there's a perception of this extreme surprise. We didn't know it all, but we did know there was uncertainty on these things. But now what's happening is we are observing the climate system in real time. We're observing this one model realization, one realization of our life in the observation record. The ultimate one that now we're comparing it against what was predicted from the past and what we have in our models. And it's revealing either gaps in our understanding, gaps in the data, or unexpected things that are happening that weren't something we were really watching closely. Like if you started to actually have the ships clean up and the cleanup happens at an accelerated pace than what was expected, what does that actually mean real time?
But is there any reason in any of this to revise our basic understanding of the science, or do you think it all, like, even though it's unexpected, it still sort of fits within our basic framework? Or should we think that we've gotten something substantially wrong because all this is happening before we thought it would?
It still fits within our basic framework. And I will add on in the conversations I have with my clients, people need to be asking questions about how their business, their life, their livelihood, how it interacts with climate and the climate we've had of the past and how changes in that may affect them in the future. And you can either look at certain scenarios about what the future looks like, or another methodology is you think about like where are your pressure points and what might break you or what might affect you. And then try and understand what are the different types of scenarios. And some of them may be climate or extreme weather. Some of them may be other types of events may affect you. And then try and understand what is the probability of that. And then how do you build resilience around those myriad of things.
Much more of like a insurance mindset. Yeah, I feel like back in the beginning, we used to have these models that would crank out these sort of very precise numbers. And we would talk about sort of optimizing toward those numbers. But I feel like we've all kind of gotten the memo now that we're not going to have that kind of precision, and we need to be doing this rather than optimizing this sort of like hedging strategy that you're talking about. Like, you know, how do we hedge our bets? What are the things that we want to absolutely not lose? Basically more of like an insurance mindset. One other stray thing, geoengineering. What's going on there? I guess I sort of wonder, like, what is the attitude of the credentialed climate scientific community toward that stuff? Are all those just like wild and crazy cowboys out there doing crazy stuff? Or is this something that climate scientists are really seriously engaging with? Like, what's the state of that discussion?
We talked at length about the ships and how ships led to change in aerosols.
Yeah.
And so that's a real world example of
accidental geoengineering.
Accidentally leading to warming and affecting local and potentially global climate as well. And with climate models, there's the ability to look at many different types of worlds and to be able to model those out and look at what those effects might be. And then there are, you know, these examples that we're starting to see of the ships. You see it whenever there's a volcano eruption. You see it after a wildfire, these local and global events. And this field of science of how, and the term I usually use is climate intervention, of how do you affect the climate knowingly And there's a wide range of this. It's how do you modify the sunlight and the solar heat, which affects temperature. There's how do you affect carbon removal from the atmosphere to lower temperatures. And so there's a myriad of these things. And I would say over the last 10 years, the science around that has evolved rapidly. And there's been more focus on it. There's been more programs on it. There's been more science happening in academia and governments. And this is happening in the US as well as around the world. And what is also starting to happen is as that science matures, we're also starting to now see startup companies, and you're starting to actually see companies acquired in the space and IPO.
Yes.
So
makes me
the
nervous.
science has rapidly evolved over the last 10 years, and the technologies are rapidly evolving, and you're starting to see the companies that are looking at this as something that might happen in the future and providing services as people are starting to seek those out. And the carbon dioxide removal is in a more mature state across all of these. And, there's even a market around carbon removal that prices how much carbon you remove. And so there is a lot of science around this, and there's a lot of discussion of where does the science go on these different things. And I see the science evolving, and I also see companies evolving around this as well.
Okay, real final question. I often joke, like, one of the things that I got really sick of when I used to talk and write and study climate change a lot is a distressing amount of the public conversation about it devolves to how should we feel about it, or how do you feel about it, or how do I feel about it, or what's our level of optimism, or from 1 to 10, just this constant psychoanalyzing of it, which I really am sick of. Nonetheless, I'm about to do it myself. We're told that we're heading somewhere between 2 and 3 degrees. That's sort of like the conventional wisdom now. 2.4, 2.6, something like that. I guess I'm just would like to hear from you. You said you don't freak out. How bad is that going to be? Basically, like 2.5, like how should we think about 2.5? Because we've been told for a long time that like 1.5 is the threshold. And we saw this report from the UNFCCC that said going up to 2 would be, all these catastrophes, all these long-term whatever. And then you go from that up to 2.5, seems like it'll be really bad, but people are acting weirdly sanguine about it. So I guess I just would like to take your temperature. How do you feel about coming in at, say, 2.5 degrees?
Society of today was built for a climate that no longer exists and is going to continue to change. And on the path to 2 to 3 degrees, the world is going to look different, very different on a climate space. The way I feel about it is we know what the climate is going to look like into that horizon. And therefore, we need to take the information that is available to us and think through and plan what adaptation and resilience is needed to deal with that. And then I'll also add, I work often in the space also of decarbonization and how does one decarbonize and thinking about that. And so there is a need to think through how does one decarbonize, because there will be pressures to do so as the climate continues to warm and we see the physical and then financial and societal effects of that.
Always a cheery topic to visit. Thank you for coming on and doing such a great job walking us through this. I feel really good. Well, not good, but I feel better educated.
I think people get nervous and they freak out because it's something that they don't know a lot about, and they don't have a framework for thinking about how to navigate through that uncertainty. And so I hope I've given you some peace with a little bit more information and thinking through how to navigate through the future.
Thank you for listening to Volts. It takes a village to make this podcast work. Shout out especially to my super producer, Kyle McDonald, who makes me and my guests sound smart every week. And it is all supported entirely by listeners like you. So if you value conversations like this, please consider joining our community of paid subscribers at volts.wtf, or leaving a nice review, or telling a friend about Volts, or all three. Thanks so much, and I'll see you next time.